guest is Bill Worzel. Bill is an expert in biologically inspired algorithms and has been leading teams in applying them to complex problems for the last 20 years. Most recently, he conceived of and began designing FogLifter, an integrated system for the Internet of Things. Welcome, Bill.
Thank you. So I'm going to talk about FogLifter, and as described, it is meant to work with the Internet of Things and allow distributed computation to be done. So imagine that this picture of the Internet is the world's biggest supercomputer, and that you control it from your mobile device. That's what we're trying to do with FogLifter. Right now, the way we use the Internet is that we go into the Internet, get information, bring it back to a data center, one or more data centers, process that data, and take the results and distribute it back into the cloud somewhere. This is roughly like trying to drink the sea dry through a straw. The IoT is going to make this model impossible to sustain. Basically, in order to find, collect, and analyze data in real time for the number of devices that we're going to have in the Internet of Things will become impossible using this model. There are n factorial ways to combine devices, and even with a small number of devices, that becomes hard to sustain. Now, this slide is actually out of date. It says that there will be 40 billion devices by 2025. The latest projections I've seen are 50 billion devices by 2020 here at this CES. Now, we've relied for a long time on Moore's Law, which says roughly that every 18 months to 2 years, the power of computing goes up by a factor of 2. So it's a straight line increase, but it's been continuing for a number of decades. The problem that we face is with this explosion of devices, and the combination of devices goes up much faster than Moore's Law. So simply put, combinatorics beats linear progression. What does this mean to us? Well, what it really means is that we have this huge wave of data that's about to swamp us in our boat, and so we need to change how we do things. Fog computing is computing at the edge, at the end of the Internet, if you will. As everybody probably knows, in modern cars, there are perhaps a dozen different processors, and most people plug their cell phone into the car. So those all become potential active devices for doing computing. Well, what's FogLifter? FogLifter is an architecture which is designed to locate, organize, and do computing on these devices in the edge of the Internet. In order to do this, we have to have developed something which is designed for intermittent connectivity because, as we all know, sometimes we go out of cell, sometimes somebody we're talking to disappears, or sometimes the battery goes dead. We want to process the data locally, but then make those results that we come up with available for people back in the cloud and in those big data centers. So what this means is by the time data reaches the data center, it will have been potentially processed 2 or 3 times. The FogLifter platform has the following components in it. It has functional relational programming, including what I call an F-code compiler and a relational rule generator and constraint checker. We'll deal with each of these in greater detail as we go along. It has a peer-to-peer connectivity module. It has a workflow description to allow us to look at what pieces we're getting from the Internet and how we're combining them. And a data registry, which says how to find them in the first place. And as is very important throughout this show, the return again and again to the question of security and privacy in the Internet of Things. So let's start at the beginning. F-code is portable code for fog computing. What I mean by that is it is code which has been compiled, which can be used in any device that has an F-code interpreter on it. So this is similar to what Python or Java does in producing an intermediate step of code. The difference is that F code is generated from functional languages. And so it has several advantages to us in this function. In particular, it enables parallel processing because functional components can be broken up and independently computed and then brought back together. So each expression can be individually evaluated, but the end result will be the same. F code uses combinators, which are mathematical operators which provide a complete set of ability to compile, run any kind of program that can be written in functional programming. So a F code compiler then takes high-level functional languages and compiles them into a series of combinators. So at the bottom of the screen here, we have a program for calculating a factorial value expressed entirely in combinators. Note that it's entirely independent of any language or any platform. So relational programming is a concept that you're familiar with, but you're not familiar with. Most people in this room are familiar with SQL and other relational databases. This is the idea of taking it outside of a database to describe how you organize information, in this case from the internet, and how it relates, one set of data relates to another set of data. And hence that we're using the relational operators, the relational algebra, and calculus to calculate how to combine and use this data. Additionally, we develop constraints on what is possible and what's allowable. And this means that we can avoid crashes and produce much more rigorous code. Peer-to-peer connectivity, we've already mentioned the fact that in the Internet of Things, things come and go because of mobility, because of poor connectivity. So we have to be able to cope with this. So what the peer-to-peer connectivity module does is it supports dynamic environments since the edge devices come and go. What it means is that we can share computation, but if you happen to disappear, the whole program doesn't fall apart. We can recover and continue to process. In other words, we're used to thinking of peer-to-peer, for instance, in sharing music files famously. But here what we're using it for is to share computational power. In addition, we need to be able to, if I'm in a data center and I want to reach out to grab data that has been partially computed somewhere in the internet and then combine it in a sensible way, we need to be able to map this problem and move the data to the right processing. So to do this, we have a workflow design, and this is an example of a diagram from the book Enterprise Data Workflows with Cascading from O'Reilly. So this is an example of putting each of the relational pieces we were just talking about in our bigger program together, hooking them together, showing where the plumbing goes, and then also identifying the places where parallel processing can be done. So every one of those blue and red dots on that image is a case where you can either map or reduce the computational flow. The data registry does two things. It provides semantic description of the data, which is to say, what does it mean? So if I'm trying to find a piece of data having to do with farming and water usage in farming, I need to be able to search for and find out what that particular node in the internet has that kind of data. And then it also has a data dictionary which explains what format that data takes. Sometimes this data may be raw data, and sometimes it may be computed data. But all of it ends up in the registry. Security and privacy are vitally important to edge computing. We must make sure that the data is safe, that people do not have unrestricted access to the data, and that the owner of the data can protect it. So it has to use heavy encryption and a number of other techniques to protect the data. In addition, as we've already heard at this conference, privacy is a very signature issue in the Internet of Things. The way I summarize it is permission must be an act of commission, not omission. you must actually say, the owner of the data must actually say, yes, there is permission to use this data. So when is FogLifter most useful? Well, first of all, when we're analyzing a high volume of data from all over the internet and we're trying to bring it back together. So a piece from here down at the edge, another piece from somewhere in another continent and another in another application. All of it has to be brought together. It's a high volume, but you have to find it and combine it. When local results require something quickly, how many people out there have been driving and seen that the traffic is bad on the highway in front of you? And so you take out your cell phone, you look at the map and see, well, is it red, is it green, is it yellow? Oh, and so you look at it and say, well, it's only yellow. It's pretty good. I'll stay on the highway. And by the time you get there, it's bumper to bumper, and you're stuck on the highway. Well, the reason for that is it had to be processed, go up, and then come back to your cell phone. If instead you could work with that in terms of on a real-time basis, using that data in real time by talking to other cars, then you might be able to respond to it immediately. The next point is when we have intermittent or low bandwidth connectivity. This is where the connectivity between devices comes and goes. People are walking around with cell phones and in a city, and they go in and out of cell. Or when it's a low-power device that doesn't have a lot of connectivity that can broadcast a great deal of distance. And then finally, when the same computations are used for multiple purposes. We'll look at each of these cases, but that's an important idea of reusing something that is calculated on the edge for multiple purposes. Let's start with the example that I mentioned just a few minutes ago. If we have, as we're starting to have in major cities, we have smart roads. The roads themselves have sensors in them. So do the traffic lights. And the cars, of course, themselves have, as we've discussed earlier, maybe a dozen computers in them. So if you are in city traffic at rush hour and you want to know if there's a better way to do it, as you can't just sort of look on Google Maps and see whether it's going to be easier to get around or not, because it's out of date. Instead, we're going to have vehicle-to-vehicle communications that is going to allow you to, on the fly, your car can recommend a route around the traffic to where you want to go. But it doesn't stop there. Because the fact that we have smart roads means that the traffic control system can integrate with where you say you're going and how you're going to travel there. And post facto, after, later on in the year, people can city controllers can analyze what the traffic patterns have been and change the infrastructure to make the traffic flow more smoothly. Now, there's a lot that's been said about the smart grid and the Internet of Things, and that is indeed one of the places where a lot of action is being taken. Everybody has smart meters in their houses, but in addition, every transformer now has a separate device in it. And so the smart grid is being built out of this kind of device. But I want to talk about something else which might come to pass, which is a little bit different from a social point of view. We all have smart houses, or more people are beginning to get smart houses that have sensors in them and lots of processors in their thermostats. They may have photovoltaics that are being regulated. They may have e-cars with batteries that need to be charged. As I said, the thermostats and so on. Well, if instead of just putting power produced out into the smart grid, we collectively in our neighborhood share with other houses, then we actually can become essentially a local smart grid. We can help each other and our neighbors, providing power to them, and we can also work as a co-op to potentially sell power together back into the grid and perhaps get a better price for it. Last example of immediacy is mall shopping. If I have my cell phone out in a mall and I see a pair of pants I like and I take a picture of it, then I might like something about them, but they're not quite what I'm looking for. if I can pool the computational power of other people with smartphones in the mall, then we can produce an image recognizer that can communicate with other stores and say, do you have any things like this? But there's also unintended consequences. In that left-hand picture where we took the picture of the pair of pants, we also got the footwear and the fact that the person was wearing a stripy shirt. So a store might also take advantage of looking at that and the image processing information that was sent to show examples of stripy shirts or other similar kinds of footwear. Home health care is something which we see a lot of at CES today. Everybody's wearing new health sensors. But those sensors, valuable though they are, actually need to be connected with your doctor's records and the e-records that are kept on you in medical records. So by using FogLifter, you can integrate the local heart information and integrate it with your electronic records that your doctor keeps. The last example is with farming. Farms are somewhat homely in a lot of high-tech conferences. But in fact, farms are at the very cutting edge of doing, using the Internet of Things, and have been for perhaps a dozen years. Basically, these days, farms now have sensors buried in the fields. And so in this case, what we're talking about was within the field, they don't have much connectivity because it's buried underground. So you actually can't send information out necessarily in real time. But what you can do is those individual sensors that are buried can talk to one another. And they can actually build up a model over time of what that field looks like. And then they can begin to talk to other fields and build up a bigger model of what the farm itself needs. Now, what do we do with that data? Well, one of the things we can do, how do we get it back, is we can literally fly an aerostat over the fields and harvest the data from the sensors. And not only the data, but it can harvest the computed model of what those sensors built. But it doesn't stop there either, because farms and farmers already have social structures like farm co-ops. So you can now take a number of different farms, gather them together, and get a model of what's happening in the local area. This can then be extended up into the higher region and affect things like crop insurance markets, the availability of farm equipment for use and sale. The information used in farming is important for a number of different purposes. In particular, you have to look at things like not only crop yields, but also things like water usage. So here we have an example of multiple people using the data from farms for different purposes. So here we have water use farming, water use planning. This has to integrate not only the use of water with farms, but the use of water from industrial purposes and, of course, for populations, for drinking water. They don't really care about anything other than what the projected water use is from farms or regions of the farm. That just becomes one part of it. Whereas if we move over, we look at agricultural market analysis, then they're interested in what yields are going to be, what the price of corn or wheat or other crops are going to be. And insurance companies have an interest in what the projected shortfall or bumper crops are going to be, because that affects the price of insurance. And finally, NGOs have an interest because they're interested in how much surplus there may be to distribute. So in summary, FogLifter changes the fog from a collection of individual devices to a dynamic computing system. FRP, Functional Relational Program, provides a common language with error control to keep us from crashing half of the Internet. Workflow designs map computation and that is described by the registry, and security and privacy controls increase the confidence of the users that everything will be used properly. So what this means is that FogLifter will allow the Internet to become part of all data centers. So the data center will not end at their door, but will go out into the Internet. And so we might call this the case of the sea coming to shore. The first components of Fog Lifter will be available in 2015, and for more information, please feel free to contact me, Bill Worzel, at billw@fog-lifter.com, or to call 734-276-9333. Thank you very much.